this explanation of the mechanism of the Coriolis force is important to realize that it's not an optical illusion, but it might not help us that much to understand in a qualitative way, intuitive way, motions in the atmosphere. And for that purpose, I would like to introduce the so-called inertia circle. We all agree that the deflection, because of the Earth's rotation, is at right angles to the motion, and for a constant deflection, a constant force, it will drive the motion, in this case I've taken 10 meters per second, into a circle, like all motions that are moving with a constant forcing, like the planets around the sun or a stone in a string will move in a circle. And so the effect of the Coriolis force on the Earth is to, if it was alone, to move objects into a circular motion. And in this case it would be 79 kilometers if we were on 60 degrees north. And just to make it more vivid, I have put in behind here a map over St. Petersburg, and as you can see, the inertia circle covers an area about the same size as Leningrad Oblast. So it's a quite small part of the globe. So one first conclusion is that if only the Coriolis force was active, air would stay in rather small parts, small regions, and have difficulties to move away from that region. And the conclusion is that it's thanks to strong pressure gradient forces coming from thermal contrast that we actually have air masses moving considerable distances. But if we stay with the pure Coriolis effect, it has some very strange consequences. And before I came to them, I will just again show you that I'm not playing with mathematics. Here is the trajectory of a buoy in the Baltic Sea in summer 1969. It starts with, on the 25th of July, there is a westerly wind pushing the water and the buoy eastward. And then suddenly the wind stops, there is no wind, but because of inertia, the water continues to move eastward. But now, just moving under inertia, it's affected by the Coriolis force and is deflected to the right in actually an inertia circle. But because there is also a major current independent of the present wind from east to west, this inertia circle will move in a spiraling westward. Now, with the typical speed of the water, 20-25 centimeters per second, and the latitude, about the latitude of St. Petersburg, Helsinki or Stockholm, the inertia circle, the trajectory without any deeper current, would have had the size of the circle to the lower right. But as you can see now, it is transported westward, but the size and also the period of oscillation agrees almost perfectly with the mathematical expectation. So this is a case where nature very carefully replicates almost exactly the mathematics. Now, another fascinating example of inertia circles is the so-called Taylor columns. So here we have a tank of water, not rotating, and we drop ink into it. And as you can imagine, the ink spreads and colors the whole water blue. That is common sense. But if now the tank is rotating, something strange happens. If we continue to drop the ink in the same position, it will just go down or move in the vertical, but not spread out. So we will have a sort of a solid looking object moving around, a blue column with the ink not spreading out. and coloring all the water. And the reason is that whenever any ink particle would like to move out, it's moving perpendicular to the rotational axis and is affected by the Coriolis force that drives it into an inertia circle, a very small one because of the rotation rate. So it drives it back to the main blue column. So it's the Coriolis effect, the inertia circles, that keep this column together, and that is a very striking example of the constraining effect of the rotation on an object. And some scientists talk about that the rotation has changed the mechanical properties of the water. It still looks like water, tastes like water, but it's sort of more tight. It's in some even talk about Coriolis stiffness. The mechanical properties of the water has slightly changed. Another fascinating example is a ping pong ball, which you release from the bottom of a tank. And without rotation, it goes up with a certain rate. But if the tank is rotating, it goes up more slowly, because when it's going up, water has to escape at the top in the horizontal and come in behind in the horizontal. And both these motions are perpendicular to the rotational axis, are affected by the Coriolis force, which tries to prevent this to happen by trying to drive the water back from where it came. So the ball has to fight more to get up now than before, and the motion upwards is therefore slightly slower. Then another interesting thing that these inertia circles help us to qualitatively understand is the wind systems on our planets. We don't know exactly what the mechanisms in the entire atmosphere of Jupiter, but if we assume that the outer parts behaves fairly similar to the Earth, with rising motion in the lower latitudes where the sun's insolation is strongest, sort of what is called a Hadley circulation, then we can seem to understand why actually the winds are strongest at Jupiter around the equator, and to understand why they are quite violent at Venus but at higher latitudes. Actually, the high speeds in absolute terms of the winds over Jupiter is because of the size of the planet, not that it is rotating fast. And also, it's a common misunderstanding that because Venus is rotating slowly, its winds have to be slow. It's actually, as I will show, opposite is the truth. And we understand this by again reminding us that the rather counterintuitive consequence of the Earth's rotation is to try to keep the air more or less where it is. I call this the woolen cap effect, that it's rather difficult to move air because of the Earth's rotation. So it has a constraining effect on the air's ability to move around, and we can use that now to understand the basic flow patterns over Jupiter and Venus. So here we have a case of high rotation, and that means strong Coriolis force. It means small inertia circles, a stronger constraining effect of the air trying to get away from the maximum heating around the equator. And but on the other hand, it is not much time to accelerate. So it will be rapidly moved into a westerly wind, and so the winds are relatively weak. And an American English scientist, P.G. Williams, have made nice computer simulations simulating the rotational effects of the atmosphere. And in this first image, he has just replicated the Earth general circulation, or at least the westerly winds in the troposphere and lower stratosphere. And what he has shown is the very well-known fact that we have a subtropical steady jet stream around 30 north, positive 50 meters per second perhaps. Around the equator, the west wind is negative, it's the trade winds. We also have the polar front jet, but since the polar front jet changes its position, it is lost in the averaging. So what remains is the more steady subtropical jet. So this is a fairly realistic simulation of the Earth atmosphere. And now he speeds up his calculations. So he is, let's say, 8 times. And of course it's much more than Jupiter, but in those days he had to amplify just to get the signal out. And here we can see that for increasing rotation, the subtropical jet draws closer to the equator, and for very strong rotations it more or less becomes an equatorial jet stream. The size, the strength of the jet stream is more or less the same, but now remember that the rotation of the planet is 8 times stronger. It means that the wind is less super rotational than it was. Super rotation means that it is moving faster than the rotation. It's still moving faster than the rotation, but since the rotation is quite high, the proportion is much smaller. So that's why we have 2 to 3% super rotational winds in the equatorial regions of Jupiter. They are strong, but they are strong because of the size of Jupiter. If we normalize it to the size of Mars or the Earth, it might just be a matter of a few meters per second. Then we have the case of slow rotation and weak Coriolis effect. That means larger inertial circle, larger radiuses. And it means that the air can move quite long distances from the equator up towards the poles before it's affected by any substantial Coriolis effect. And during that acceleration it can also reach high values. So what we again can see now in Williams' simulation is now how the subtropical jet has moved far away from the subtropics, almost up to the Arctic. It's still about the same size, 50 meters per second or 80 meters per second, but now it's a case of very slow rotating planet, so it's highly super rotational. And this is what we can see at Venus, in the atmosphere of Venus, very high winds close to the poles. So in a qualitative sense, this helps us to understand the wind systems of the Earth, Jupiter and Saturn and Venus. Then another thing we can understand is the geostrophic wind from a new angle. And this is my favorite way to derive it. It's actually done by the French Academy in 1859. They were discussing, they had just realized that the Earth rotation is important and the Coriolis effect, and now how would that affect the water in the sand? Because in springtime, when the snow is melting in the Alps, the sand will move faster, and is it now a risk that it will flood the right bank in Paris, for example? So here we have the Seine under calm conditions, but now there is water moving into the picture. It has a certain weight, and this speed of course creates a Coriolis deflection to the right, which accumulates water to the right and less water to the left, so the sand will have an inclining surface. And we can make some simple mathematics. We have an expression for the weight, for the Coriolis effect, and they together constitute a force that is perpendicular to the surface of the sand. So simple mathematics, simple geometry tells us the fraction the inclination of the surface is the same as the fraction between the Coriolis force and the gravity. So what we have here is a simple derivation of the geostrophic wind. Now, the French Academy didn't quite understand what they had done, so when some years later another scientist came with a derivation of the geostrophic wind. This paper was refused, unfortunately. So the first European who derived the geostrophic wind was Norwegian Henrik Mohn. Then we can think if we have now what is called a stratified fluid, we have the Seine water but in two different densities. Then the intermediate surface will slope, incline slightly differently. And this applies to our understanding of sloping fronts, warm fronts and cold fronts. They have a typical slope of 1 to 100, 1 to 50, perhaps 1 to 200 in the atmosphere. And that is a consequence of the Earth's rotation. And by applying the same type of mathematics, we can derive the inclination, tangents of alpha. And alpha is the slope angle of a front. And this formula is called Margulis equation. And we can understand intuitively from this example, we have cold air to the left, warm air to the right, and if they now are free to move, of course the cold, heavier air will come down in the bottom, the light, warm at the top, so it will be a motion, but in a rotating system, the Coriolis effect will try to draw it back from where it came. So what you will have now is a compromise or balance between one force trying to equalize and one force that is trying to restore back the original conditions. And here's another way to illustrate that. You have cold air or cold water, and light air or water, and then you have a separating wall, and you lift that, and there is an equalization. But if there is now a rotation, this counter effect of the Coriolis force will try to restore the initial conditions, and you have a balance between these two conflicting forces, and depending on the differences in density and the strength of the Coriolis force, this slope will be stronger or more or less pronounced. And this is regulated in this formula derived by Max Margulis, an Austrian meteorologist, more than 100 years ago. Then finally, we can also understand qualitatively what is happening in the tropics. The Coriolis force is dependent on the latitude, and it's the fact that it is zero at the equator, and of course very weak close to the equator. On the other hand, the wind currents and ocean currents in the tropics are very steady. So even if the Coriolis force is weak, just because of the steady forcing, it must still have an accumulated effect on the atmosphere or the ocean. So here we have, first of all, the El Niño. It's warm water that is transported by the trade winds towards the Indonesian archipelago. So there's generally a seawater temperature maximum in the westernmost equatorial Pacific. And then what happens is that in the phase of La Niña is opposite to El Niño, where you have cold conditions in the east of the Pacific. You have still the trade winds. The trade wind is keeping the warm water in a sort of upslope over the Indonesian archipelago. But then something very interesting happens in the East Pacific. You will have the Coriolis force on the trade will deflect slightly to the right, to the north, to the left in the south. That means causing the water, so the wind is forcing the water westward, the Coriolis effect is moving the water north of the equator to the north, and south of the equator move the water to the left. That means a divergence of the upper water. A divergence, and compensating water from deep under comes up. So what you will see, and I will show that shortly, a very narrow cold zone exactly on the equator. So it means that by an infrared glasses you can actually see the equator from outer space. I will come back to that later. Then El Nino happens partly because the trade winds change and the winds now move the warm water eastward. But again, the Coriolis effect plays a role because the warm water moving eastward could very well float out. But because of the deflection to the right or the north of the equator, to the left, south of the equator, the Coriolis force helps to keep the warm water rather concentrated. So it hits Peru and this part of South America with full force, partly thanks to the Coriolis effect. So shows that even if the Coriolis force is zero or very small at the equator in the tropics, it still has a profound effect on the dynamics. And here are some images just to prove my point. The upper one is La Nina conditions with the warm water over the Indonesian or Western Pacific and the cool water over the East Pacific in a very narrow zone along the equator. And under normal conditions, there is no pronounced cold zone along the equator in the east, but you can still see that the minimum temperature is straight on the equator. And then the lowermost picture is when the El Nino has happened and the water has spread from west to east over the whole of the Pacific, but is still rather concentrated along the equator. So, thank you very much.